right, first of all, let's talk about this little sentence I put here. For the next three problems, the resultant vector to hold or move an object that's on an incline, like a ramp, is always perpendicular to the incline. So why are these always going to be right triangle problems? Because the vector needed to hold, the resultant vector that holds the object on the incline is perpendicular to the incline, which gives you a right triangle, but it's kind of slanted, a slanted right triangle because it's perpendicular to something that's slanted. So that makes it a little tricky. Okay, let's look at this problem with this tortoise. Workers at the Audubon Zoo must move a giant tortoise to his new home. Find the amount of force required to pull a 250-pound tortoise up a ramp leading into a truck. The angle of elevation of the ramp is 30 degrees. So the thing that's interesting here is that the vector is the same whether it's, the force is the same whether you're just keeping it there on the ramp or having it actually move up the ramp. Does that seem weird that it's the same force either way? It just is. I guess it's because once you get it going, that's just the force that's needed. So, okay. So here's the tortoise on the ramp. The ramp is a 30-degree angle with the ground. Why do we have a line coming straight down? What does that represent? That's the weight of the tortoise, because weight, like I said a few minutes ago, is just the force of gravity acting on the mass of an object. So the gravity acting on the tortoise is 250 pounds toward the center of the earth, which is where gravity acts. Okay, so now here is the resultant vector, which is the vector required to hold or move an object. So we're trying to find the amount of force required to pull a 200-pound tortoise up a ramp leading into a truck. So let's try and understand this better. There's gravity acting on the tortoise. Somebody's pulling the tortoise into the truck. We need this much force. When the question says how much force is required to pull the tortoise up the ramp, which force are we talking about? The one that's needed, the resultant that's needed, or the force that's actually being pulled up? Yeah, the force that's being pulled up this way. That's what we're trying to find, X.
What is the result?
Huh?
What would the result be? I mean, like, what does it mean?
The resultant means the force that's required to keep an object there.
Oh.
It's just, it's not like it's an actual thing. This is, I mean, these are all forces, which is different than an actual item, like the actual side of a triangle. They're all kind of, I don't know. Addison, explain it for me. Never mind. So it's not like there's an actual object there of any kind. It's just that this force plus that force have to equal this force in order for it to work out. Okay. So then, notice how they've drawn in the dotted lines. If you have to draw your own picture, you would be putting the parallelogram in yourself. So some of these pictures are already drawn for you, which is nice, but you also need to get used to being able to do them by yourself if needed, okay? Anyway, okay, so the parallelogram's been drawn in there. That means if this side is length x, what's this side down here? This is x, good, because, and that's what we're trying to find, is the x, the force that direction. We know that number. We need an angle somewhere.
I know all the angles.
Okay, Addison says he can help us out with the angles. I'll let him help us.
They're all 30 to 60 angle triangles. Yeah, I got it.
Well, they're not, well, all of the triangles in this picture are 30, 60, 90, but they wouldn't be unless that was a 30. It is a 30, but yeah. But depending on the problem, like the next problem is a 10, so the angle is going to be a 10.
Right.
Anyway, since this angle is 30, Addison is saying that this angle is also 30. How do we know that?
Why are you looking at me?
Do you want me to explain why that is true, or do you just want to trust it?
You should explain it.
That's what I thought. Okay, so this angle is made with the ground, right? So that's a, if we had a wall there, that would be a 90-degree angle. Okay. So here's another 90 degrees here. That means that this angle is 90, right? And the weight vector goes straight down from the turtle, which means it is 90 degrees with the horizontal ground. Okay, so we have this little teeny triangle in here. This angle is 30. That angle is 90. That means that angle has to be 60. This total angle is 90. So if that angle is 60, this one has to be 30. So it just so happens that the angle of the ramp is always going to match the angle between the weight and the resultant. Always.
Wait, so it's always to the ground angle and always.
This ground angle and this angle between the weight and the resultant will always be the same. So like in the next picture we're doing, this angle right here will be 10 because the ramp is 10. Okay. All right. So that angle is 30. This side is 225. We want to find this side. We could use law of sines because we have an angle and we're trying to find that side. And do we have this angle here? Yeah, it's 90. So we have that angle and that side, right? So you could use law of sines. So you have sine of 30 over x equals sine of 90 over 250. And of course, sine of 90 is just 1. So that's why it ends up working out just fine. But anyway, or we can just use SOHCAHTOA. So I would prefer that. So across from the angle is the side we're trying to find. The other length we know is the hypotenuse, correct? So we have opposite and hypotenuse. Which one would that be? Sine. So I could actually do the sine of 30 is x opposite over 250 hypotenuse. So x is simply going to be 250 times the sine of 30. Please don't need a calculator for this one. Please. Don't bother using your calculator. Sine of 30 is 1/2. Sine of 30 is 1/2, which means the resultant, not the resultant force, but the force needed to pull that up is 125 pounds of force. That's quite a bit of force. It's a pretty big tortoise, whatever he is. Is that the only question we had to answer on that one?
Yes, sir.
Yeah.
Kind of cool. So anytime it's a 30-degree angle, you just gotta look at that.
Yeah, if it's sine, if it was a cosine problem, then that wouldn't work because cosine is square root of 3 over 2. It would have to be the opposite side.
Okay.
Because see, it's a 30, 60, 90 triangle, like Addison said. So if the hypotenuse is 250, then the short leg is half of that. You could just use your 30, 60, 90 rules and do it that way. Yeah. Okay. Next one. If a force of 86 pounds is required to push a safe up a ramp, so now they're actually giving me the force to push it up the ramp, and they're saying it's 86 pounds. If a force of 86 pounds is required to push a safe up a ramp that is inclined 10 degrees, then what is the weight of the safe? So this time, x is what piece?
Weight.
X is the hypotenuse, right? Because it's the weight. So the weight is always the hypotenuse. All right, and we know that the force required to push it up the ramp is 86 pounds, so that means this little piece of our triangle down here is also 86 pounds. What do you think? Can you guys solve this on your own? Try it out for a second. This angle of the ramp is 10 degrees, so the angle up here in our triangle is also 10 degrees. Everybody try this on your own. See if you can get the right answer without my help. You can use either law of sines or you can use SOHCAHTOA. And it's not quite as simple as the last one because it's not sine of 30.